Hello everyone, good evening. Okay. So today we will be starting with the subject of process fluid mechanics. So I hope I'm clearly audible and the slides are visible too. So fluid mechanics, or you can also call it as process fluid mechanics, or in other universities they also refer to it as fluid flow operations. So all of these subjects basically deal with the study of the behavior of the fluid either at rest or in motion. So if the fluid is at rest, then we call that study as fluid statics. And if the fluid is in motion, then we call it as simply what fluid flow operations. So this course covers this fundamental concept of fluid statistics and motions, including governing equation that describes the basic principles related to this fluid statics and motion. Then another important topic from gate perspective also is this pressure drop calculation for a tubular flow and flow in packed beds of solid particles. So this subject you might have also partially covered it in this mechanical operations. So pressure drop calculation across tubular flow, it might include this laminar flow, turbulent flow, all the friction factor terms, all the similar concepts will be included in this, including the Bernoulli's theorem, energy balance, all those conservation balances. Then the ultimate goal of the subject is to application of the basic knowledge of fluid mechanics in understanding the momentum transfer based unit operations. So just for an example, in all of these processes, we can see the fluid flow operation, infiltration, agitation, air particle separation. So these are some of the applications in which we can utilize this knowledge of our understanding of the fluid mechanics. So from GATE point of view, so if you see in the GATE syllabus, this part is covered in section 3, which is fluid mechanics and mechanical operation. And this first paragraph covers all the topics related to fluid mechanics. That includes fluid statistics, surface tension, Newtonian and non-Newtonian fluids. So this is an important topic from objective point of view. Then transport properties, shell balances, including differential form of Bernoulli equation. This is also an important topic. Then equation of continuity, equation of motion, equation of mechanical energy, this friction factor, dimensionless analysis and similitude, flow through pipeline system, velocity profile, flow meters, pumps and compressors. So ultimately, all of these subjects, all of these topics will be covered in the fluid mechanics subject. So we will be dealing with all these topics in the coming sessions. So we'll be solving questions related to each of these. So just for the reference, so there are many courses related to this fluid mechanics available on NPTEL, and in chemical engineering, for the chemical engineering field also, you can see multiple courses related which will cover this fluid mechanics and fluid flow operations. So one such course is this web content. So here you can find notes and slides related to this fluid mechanics subject. It is from Dr. Nishit Verma from IIT Kanpur. Then the another subject which has this video course. So video contents, I think in 20-30 minutes long are available on in this course. So the course is Fluid Flow Operation by Dr. S.K. Majumdar from IIT Guwahati. And the other courses you can find it using the NPTEL website. You can find these fluid flow operations in other subjects also. For example, in mechanical engineering also they will be covering these fluid flow operations. But these two courses are from chemical engineering department. So we will just quickly cover within 5 to 10 minutes the basics of the questions that we are about to solve today. So the first question arises, what is fluid? So as per definition, fluid is any substance that continues to deform or move under the application of the shear force. So let's say if I'm having a object over here, let's consider it a 3D object. Now, if at this surface, let's say I'm applying force on this side, then due to this force, there can be a deformation in this object. So this kind of force, let me call it a shear force. And so if this object is solid, then the object will try to resist this shear force, and ultimately it won't deform and the shape would be retained to the original one. So the object would provide resistance whenever any force is applied to it. But whereas in case of fluid, the fluid will resist, but it will continue to deform under the application of the shear force. So there will be a permanent deformation in case of fluid. And fluid at rest cannot sustain a shear stress. So under the effect of shear stress, it will deform. That is what this means to say. So fluid resists deformation by attaining an equilibrium rate of deformation. So as soon as some kind of force is applied, there will be deformation in the fluid. And the property of the fluid due to which it resists, which relates its resistance to the applied shear force, is known as viscosity. So due to this viscosity, there is permanent deformation, or the resistance is applied to the shear force in case of fluid. So how do we correlate the viscosity with shear force or the strain rate? That is basically the deformation that is occurring. So that is given by this equation. So this equation you can write it as tau is equal to mu dvx by dy, where this tau is the shear stress that is applied. Mu you can call it as apparent viscosity, and dvx by dy, basically this is the velocity gradient, that is a change in velocity occurring with respect to the y. We call it as strain rate. So this equation correlates the shear stress with the strain rate, and the proportionality constant is, we define it as viscosity. And in general, this viscosity terms depends on this velocity gradient and also the temperature. So based on the temperature, the viscosity will vary. There are equations that correlate temperature with viscosity, and I think that you will study in transport phenomena subject. So for Newtonian fluid, mu is equal to mu T. For liquids, viscosity increases with temperature. For gases, viscosity decreases with temperature. So these are two important points. And again, if we are having Newtonian fluid, then the velocity gradient won't play a role, and the viscosity will be only the function of the temperature. So for Newtonian fluid, viscosity is only a function of temperature. And for non-Newtonian fluid, we can write this correlation, that is mu. For non-Newtonian fluid, we can write this correlation. So this correlation, we also call it as power law model. So the power law model correlates the strain rate with that of the viscosity, with that of shear stress. And this equation is only valid for non-Newtonian fluid. And the other terms in this are, m is the flow consistency and n is the flow behavior index. So based on the value of n, we can comment on what kind of non-Newtonian fluid it is. Again, this equation is known as power law model, and this entire term is known as apparent viscosity. So we can write this mu as m dvx upon dy raised to n minus 1. So this is our formula for apparent viscosity that comes from the power law model, and this will be useful in solving many numericals and also commenting on the rheological behavior of the fluid for this non-Newtonian fluids. So if we make a plot of this shear stress, that is tau, with the strain rate, then we get this kind of graph. So basically these are different kind of non-Newtonian fluids over here: Bingham plastic, pseudoplastic, and dilatant fluid. And then there is this Newtonian fluid. So for Newtonian fluid, it will simply follow the equation tau is equal to mu dvx upon dy, and for Newtonian fluid, mu will be a function of only temperature. Now there are different kind of fluids where this viscosity will depend on the strain rate. That is, mu is a function of temperature as well as strain rate dvx by dy, and such fluid are known as non-Newtonian fluid. So over here, the first one is the Bingham fluid. So in Bingham fluid, there is this minimum yield stress beyond which only the fluid will start to deform. So that is, fluid does not move or deform till there is this critical stress applied. So once we have this stress above tau naught, then only the fluid will start to deform. Then the other kind of fluid is this dilatant fluid, that is given by this equation tau is equal to some constant raised to dvx upon dy raised to n. So if n is greater than 1, then in such a case we can call the fluid as dilatant fluid, and the graph you can see as by this plot over here. And if n is less than 1, then such a kind of fluid we call it as pseudoplastic fluid. And if n is equal to 1, then this equation will simply become the equation for the Newtonian fluid, and that implies the fluid is Newtonian. Apart from this fluid, there are also this time-dependent fluid. So there are two kind of time-dependent fluid. One is rheopactic thixotropic fluid. So in this case, the viscosity or the strain rate will depend on the time until which the shear stress is applied. So until now we studied, in the previous slides we studied about fluid and types of fluid. Now let's say if I'm having fluid, so this is a fluid just kept stationary, then all the studies related to this are known as fluid statics. And so in this we have to identify all the forces, that is the pressure force, external body force. So gravity can also be applicable on this fluid. And once we do this pressure balance, once we do this force balance, then we can get this form that will give us the information about the fluid which is at rest. So this equation is important. Delta P plus rho G is equal to 0. And in scalar form, you can just write it as delta P by delta Z plus rho G is equal to 0. This you can also remember it by P plus rho G H is equal to 0. So this is the pressure due to height h of the fluid. So let's say if I'm having a tank and fluid is filled till height h, then the pressure at this point due to this fluid will be rho gh, and above which atmospheric pressure might act. So the pressure at this bottom will be Pa plus rho gh. So this is the short introduction to fluid statistics. So now let's start solving few of the numericals. If you have any doubt, you can just unmute yourself and ask, or just write it in chat box. So we will be solving questions related to this power law equations given by this equation. So this equation we have to remember. Then different kind of fluids, and few questions related to fluid statistics. So yes, the first question is question number 10 from GIT 2013, and the question is the apparent viscosity of a fluid is given by this equation where dv by dy is the velocity gradient, the fluid is dash. So here we have been given the apparent viscosity. So we have this power law model for non-Newtonian fluid. We can write it as tau is equal to, let's say, some constant m, then the strain rate or the velocity gradient dv by dy raised to n minus 1, and then we have dv by dy. In this term, we defined it as apparent viscosity. So this m is a constant, and based on this value of n, we can comment on the rheological behavior of the fluid or what kind of fluid it is. So if n is equal to 1, then it is Newtonian fluid. If n is greater than 1, then it is dilatant fluid. And if n is less than 1, then it was pseudoplastic fluid. So we need to find the value of n, and then we can select the option. So we will just compare this equation with this. So m dv by dy raised to n minus 1. Over here we have been given as 0.07 dv by dy raised to 0.3. So over here we can see that n minus 1 is equal to 0.3. That implies n is 1.3, which is greater than 0, which is greater than 1. And since it is greater than 1, we can see that the fluid is dilatant fluid. For Bingham plastic, we have the form of this form, tau is equal to tau naught plus mu dvx by dvy. And since we haven't been provided this form, Bingham plastic is not our correct answer. For pseudoplastic, n should be less than 1, so this is also incorrect. And for thixotropic, the shear stress, the strain rate would be time dependent. And we haven't been provided any time sensitive information over here, so this is also an incorrect answer. So the correct answer is this dilatant fluid. Now, this is this next question from GATE 2014, Chemical Engineering. And this question is, which of the following options are correct? So for a heopactic fluid, the apparent viscosity increases with time under constant applied stress. So yes, heopactic fluids are time-dependent fluids and their apparent viscosity increases with time under constant applied stress. So the first option is the correct one. So second option is for a pseudoplastic fluid, the apparent viscosity decreases with time under constant applied stress. So this pseudoplastic fluid is time independent fluid, so the viscosity won't change with respect to time. So this option is incorrect one. Then the other option is for a Bingham plastic, the apparent viscosity increases exponentially with deformation rate. So for the Bingham plastic, the equation was tau is equal to tau naught plus mu dvx by dvy, where mu is not dependent on this deformation temperature. It won't increase exponentially with deformation rate. So this is also an incorrect option. Then the last option is for a dilatant fluid, the apparent viscosity increases with increasing deformation rate. So yes, option S will be correct one, because for dilatant fluid, the viscosity will be function of this form, mu is equal to dv by dy raised to n minus 1. So this is our deformation rate and it will vary with this. So from the given option, we can select option D as the correct one. That is, P and S are the correct options. Now, we will look on this question number 38 from GATE 2018. So in this question, we have been given at a shear rate of 10 second inverse, the apparent viscosity of a non-Newtonian fluid was found to be 1 Pascal second. At a shear rate of 100 second inverse, the apparent viscosity of the same fluid was found to be 0.5 Pascal second. If the liquid follows the power law behavior, the apparent viscosity at a shear stress of 10 Newton per meter square is dash. So in this question, we have been given this shear rate. Basically, we have been given dv by dy, and then we have been given this apparent viscosity also for this case. Then similarly for other case also, we have been provided the same information, and we have been asked that if the shear stress, that is tau, is 10 Newton per meter square, then what will be the apparent viscosity mu for that case. Okay, so let's take a look on the video solution for this question. We are solving question number 38 of GATE 2018 chemical engineering paper related. The question is, shear stress, that is tau, will be equal to apparent viscosity times dvx upon apparent viscosity times strain rate. And apparent viscosity, we can write it as mu naught dvx upon dvy is to n minus 1 dvx upon dvy. Okay, now over here we have been given two different scenarios. So let's just write for case 1, the shear rate, that is basically this term dvx upon dvy, we have been given as 10. That is dvx upon dvy for first is 10, and the apparent viscosity is 1 Pascal second. Basically this term we have been given it as mu is equal to 1 Pascal second. Now for the second case, we have been given dvx upon dy for second case is equal to 100, and the viscosity of the same fluid was 0.5. It is mu equal to 0.5. Now we have to find the apparent viscosity at a shear stress of 10 Newton per meter square. So the apparent viscosity is mu naught dvx upon dvy raised to n minus 1. So we have to find this value when the shear stress, that is tau, is 10 Newton per meter square. So for that, we need to find the value of mu naught and n. Then we can replace it in this equation to find the value of shear stress. No, to find the value of the apparent viscosity at a shear stress of 10 Newton per meter square. So let's just first utilize the information provided by this case 1 and case 2. So for that, we can write the relation between this apparent viscosity as, let's say, mu2 on mu1 is equal to 0.5 upon 1 is equal to mu naught upon mu naught, that is the same, and dvx by dvy for second case was 100, and for first case it is 10 raised to n minus 1. This will get cancelled out. From that, we will be having 0.5 is equal to 10 raised to n minus 1. Now from here, we have to find the value of n minus 1. So we can take the log on both the sides, and ultimately we will be getting the value of n minus 1 will be minus of 0.3. So the value of n will be 1 minus 0.3, that is 0.7. So using any of the case 1 or case 2, we can find the next value, that is the value of mu naught. So over here, let's just use this the information from case 1, that is mu 1 Pascal second is equal to mu naught raised to dvx upon dvy raised to n minus 1. 1 is equal to mu naught, strain rate was 10 raised to n we found out as 0.7, that is minus of 0. So from here we will get the value of mu naught as 1 upon 10 raised to minus of 0.3. So this will come around 2. The value of mu naught is 2. Now we have to find the apparent viscosity for a shear stress of 10 Newton per meter square. So for that, first we need to find the value of the shear strain. Now the strain rate at this 10 Newton per meter square, that is we have to find dvx by dy. Now this we have to find. So for a shear stress of, let's say, tau is equal to mu is the apparent viscosity, 1 dvx 1 dvy raised to n we can write, and tau we have been given as 10 is equal to the value of mu we found out as 2. So it will be mu naught times of dvx by n raised to this term. Okay, so over here it will be in this mu naught. dx dx and is to n. So the value of n is already 0.7. Using this, the value of dvx by dy raised to 0.7 will be 10 upon 2 is equal to 5. So dv by dy will be 5.17, and we can solve this and found out that the strain rate will be 9.966. Now we have to find the apparent viscosity, that is mu in this case. So mu is mu naught dvx upon dy raised to n minus 1, and we will replace all the values, that is 2. From here we have this value 9.96 and n was 0.3, so n minus 1 will become, n was 0.7, so n minus 1 will become 0.7 minus 1. So we can solve this, and the value of mu, that is apparent viscosity, will be 1 Pascal second. So the final answer we will write as 1. I hope that question related to calculation of apparent viscosity given different cases of this shear rate and this apparent viscosity, given different cases of this shear rate was clear. We can move on to the next question. So this is question number 27 from GATE 2021. And the question states that consider a fluid confined between two horizontal parallel plates subjected to shear flow. In the first experiment, the plates are separated by a distance of 1 mm. It is found that a shear stress of 2 Newton per meter square has to be applied to keep the top plate moving with a velocity of 2 meter per second while the other plate is fixed. In the second experiment, the plates are separated by a distance of 0.25 mm. It is found that the shear stress of 3 Newton per meter square has to be applied to keep the top plate moving with 1 meter per second while the other plate is fixed. In the range of shear rates studied, the rheological character of the fluid is dash. So here we have been given two experiments which involves two horizontal plates, and we are moving one plate, and corresponding to that we have been given this shear stress and the velocity change occurring, and based on this we have to comment on the rheological character of the fluid. So what we will do is, given the information, we will try to fit the power law model. So we will try to fit this using the given information, find the value of n, and then we can find which of the following option is the correct one. So I will just quickly share the video solution. First experiment. Over here we can see that we have been given two horizontal parallel plates. Let's say this is our top plate and this is the bottom plate. So in the first experiment, the plates are separated by a distance of 1 mm. So this is the first experiment. And this distance is 1 mm. It is found that the shear stress of 2 Newton per meter square has to be applied to keep the top plate moving. Let's say tau we have been given as 2 Newton per meter square. The top plate is moving, whereas the other plate, that's the bottom plate, is fixed. So let's just consider this as fixed. And this plate is moving in, let's say, x direction. This is y direction. The velocity is 2 meter per second. Now in the second experiment, we have been given the plates are now separated by a distance of 0.25 mm. Now the distance is 0.25 mm. Shear stress applied is 3 Newton per meter square with a velocity is equal to 1 meter per second, while the other plate is fixed. Now we have to study the rheological character of the fluid. So that we can study using the power law equation that states that tau is equal to mu naught d velocity is in x direction, that is dvx dy raised to n minus 1 dvx on dy. So based on the value of n, we can comment on the rheological character of the fluid. So basically, if n is greater than 1, that implies the fluid is dilatant fluid. If n is less than 1, that implies it is a pseudoplastic fluid. If n is equal to 1, then we can say it is a Newtonian fluid. And if there is any other form of this tau, then it won't lie in this three category. So to find the rheological character, we need to find the value of n. So for that, we will be using the provided information. So first we have been given the change in the velocity that is occurring. So initially the velocity was 0, then we were applying the shear stress of 2 Newton per meter square, and then the velocity become 2 meter per second. So from that we can calculate this strain rate, or you can say this value, or the velocity gradient, and then replace it in this equation with the desired data that has been provided, and then find the value of either mu naught or n. So let's do that. So first we need to find the value of this dvx by dy. So let's just consider this dy is very less, so we can write this derivative as delta v upon delta y. So that is basically, we can write v2 minus v1 upon delta y is basically this distance. So you can just write it as y. So we will be using this. Now for case 2, for both the cases basically, we can write this tau1 is equal to, let's just club both of this, and we can write this as mu naught dvx by dy raised to n. Now value of mu we don't know, and dvx by dy for case 1 we can write the velocity was 2 meter per second, that is still 2 upon 1 mm is 10 raised to minus 3 meter raised to n, and the shear stress applied was 2 Newton per meter square. Similarly for case 2, we can write this as mu naught, the velocity is 1 meter per second, for now distance becomes 0.25 mm, that is 0.25 into 10 raised to minus 3 raised to n, is equal to shear stress is 3 Newton per meter square. Now we can take the ratio of 1 and 2. So we will be having tau 2 upon tau 1 is equal to 3 upon 2 is equal to 1.5. This will become, so both of these terms will get cancelled out, and we will be having 2 into 0.25, that is 0.5, that will become 1 upon 0.5 raised to n is equal to 2 raised to n. So from this we can take log and find the value of n, and it will become n is equal to 0.584. So since the value of n is less than 1, we can write that the fluid is pseudoplastic. So this implies that the rheological character of the fluid is pseudoplastic. And from the given option, we can select option B as the correct one. Let's move on to next question. In this question also we studied the kind of fluid by using the power law model. So in most of this question, we have to use the power law model to find the value of n, and then we can find which kind of fluid which category of the fluid does it belong to. Or in other kind of question, using the power law, you have to calculate the apparent viscosity. That is also possible. Now let's take a look on next two questions. So this question is question number 39 from GIT 2022. So the question is, consider a horizontal rod of radius AR in a stationary pipe of radius R. The rod is pulled coaxially with at a constant velocity V as shown in figure. The annular region is filled with a Newtonian incompressible fluid of viscosity mu. The steady state fully developed axial velocity profile in the fluid is given by this equation, where R is the radial coordinate. Ignoring the end effects, the magnitude of pulling force per unit rod length is dash. So we have to find the force F required to pull this rod. So let's take a look on the video solution. Less than 1, the annual of viscosity. Basically, question, we have been given a rod of radius AR. So this rod has radius AR, and it has been placed inside a stationary pipe of capital R. So for this, the radius is R. Now this internal rod is pulled with the constant velocity of V, and the annular region is filled with a fluid of viscosity mu. So for this, we have to find the magnitude of pulling force per unit length. So basically, we have to find what is F, and length is equal to 1. So if this is our Z direction, we can write the shear stress between this as tau Rz is equal to, it will basically force upon area is equal to minus of mu dVz upon dr. And we have been asked to find the value of force, so it will become F is equal to minus of mu A dVz upon dr. The contact area will be the surface area of this cylinder, So basically that is 2 pi RL minus of 2 pi, and R we can write it as AR, and length we have been given it as 1, and we have to find this strain rate dvz by dr. So in the given question we have been provided that the velocity profile is given by this equation, that is UR is equal to V ln of R upon R on ln of A. Now to find this velocity gradient of the strain rate, we can just differentiate this equation with respect to R, and we will be having U upon dr is equal to V upon ln of A d by dr ln of R on R. So this will become V upon ln of A into 1 upon R upon R into 1 upon R into 1. So the strain rate will become dV upon dr is equal to V upon R ln of A. Now we will be putting this in this equation, of course, so it will become F is equal to minus of 2 pi AR into 1 into, we find that dvz upon dr is V upon R ln of A. V upon R ln of A. If R is equal to AR, we will be having F is equal to minus of 2 pi AR V upon AR ln of A. I think we are missing something. Okay. Over here, we also have this mu. So the value of force will become minus of 2 pi mu V. This will get cancelled out on ln of A. Now from the given option, we can see that the option B corresponds to the answer that we found out. That is, the magnitude of pulling force per unit length is minus 2 pi mu V upon ln of A. So we will select option B as the correct one. So in this question, we calculated the force required to pull this rod out. So yes, given a horizontal rod of radius AR within this stationary pipe of radius R, we calculated this force. Now let's take a look on our next question. Now we will be covering the questions related to fluid statics. So let's just cover this question for today. So this is question number 41 from GATE 2021, and the question is: consider a tank filled with 3 immiscible liquids A, B, and C at static equilibrium as shown in the figure. At 2 cm below liquid A, at 2 cm below liquid AB interface, a tube is connected from the side of tank. Both the tank and tube are open to atmosphere. At the operating temperature and pressure, the specific gravities of liquid A, B, and C are 1, 2, and 4 respectively. Neglect any surface tension effects in the calculation. The length of tube L that is wetted by liquid B is dash centimeter. So over here, we have been given this tank which is filled with this 3 fluid A, B, and C. And then at 2 centimeter below this liquid AB interface, this is 2 centimeter, we are having this pipe at 60-degree angle, and we have been asked to find the length of the pipe until which it will be wetted. So until what level will be this pipe filled, that we have been asked to find. So for that we have been provided the specific gravity of the liquid A, B, and C. So rho A is 1, rho B is 2, rho C is 4. So we can consider this interface. This is our reference level. That is where H is equal to 0. And using this reference level, we can write the pressure balance on both the sides and equate them to find the required length. So at this surface, we can see that on the left hand side, let's just consider this as, so over here the pressure is PA, atmospheric pressure will be acting. So the total pressure at this point will be PA plus density rho GH for this A fluid. So it will become rho A G height of the A fluid plus then pressure due to this B fluid will be rho B G HB, and this will be equal to, over here also we will be having an atmospheric pressure, that is PA plus rho GH, and we have to calculate this height H. So this is 60 degrees, so this will become 30 degree. So this entire height will become L times sine 30. L sine 30. So the pressure due to this fluid over here will be rho GH, and where H is L sine 30. So that will become rho C G L sine 30. Now this will be, pressure will get cancelled out, and this gravity also we can take common and cancel it out. So ultimately that will be rho A HA plus rho B HB is equal to rho C L sine 30, and we have been asked to find this value of L. So rho A we have been given as 1. Let's just keep this height in centimeter only, no need to convert it in meter because we are having this length on each of either of the sides. So the height of the fluid A over here is 4 centimeter. Then rho B we have been given as 2, and the height of the B above this reference level is 2 centimeter. Then over here also we are having this B fluid. So this was B. So rho B we have been given as 2 into L into sine 30 will be 1 by 2, that is 0.5. So this will be equal to 4 plus 4 is equal to 2 into 0.5 is 1 is equal to L. So length will be equal to 8 centimeter. So until 8 centimeter this pipe will be wetted. So that is our final answer. So the final answer is 8 centimeter. I hope all the questions covered in today's class are clear. In the next class also we will cover this example related to manometer, and then we will move on to fluid dynamics or fluid in motion. So to summarize, we studied these two important things. The first one is the power law model that is given by this equation, and based on this equation, questions usually related to finding the rheological character of the fluid based on this value of N are very common. Then we have to calculate this apparent viscosity given various different experimental scenarios in which we are moving different plates to generate this strain rate. That is also one kind of question that is usually asked in GATE. And then this graph also we need to remember. There are questions related to this graph also. And then in fluid statics, you can just simply remember this equation: E is equal to rho GH is equal to 0. Or you can also remember this equation: gradient of P plus rho G is equal to 0. So these two equations are important. So if you don't have any questions, we can end today's class. Okay, so thank you for joining. We can end today's class.